this is to recap what we did in class sometime before with the simple base bias board. It has a little BC109 transistor on the back, and it has a variable 2 million ohm resistor in the base lead. Has a 100 k ohm in series with the 2 mega ohm, of course, to not allow you to be able to put the full VBB across the VBE junction. Otherwise, of course, you'd damage the transistor. So always a good thing in circuits to have a safety resistor in series with a pot like this, so that when you do take that pot down to 0 ohms, you do not get the full allowable current to flow. A little bit of current limiting in the circuit there. Pretty good design. 4.7k resistor in the collector, 2 microfarad capacitor in the base electrolytic, 1k in series with that, and hooked up into that at the moment I've got the signal generator at 1 kilohertz. Got the oscilloscope set today for RMS, and channel 2 is in blue, channel 1 is in yellow. Channel 1 is currently set for 2 volts per division, peak to peak, and channel 2 is set for 20 millivolts per division, peak to peak. And I've got the readouts on the oscilloscope displayed there in RMS. So if we look at that, we've got 21 millivolts RMS going into the amplifier from the signal generator, and we've got about 1.5 volts RMS coming out of the amplifier. Now, this is a little bit crook. You can see here major distortion. Look how pointy this is here, and look how broad it is at the top. And I'm not even going to go ahead and change the bias yet. I just wanted to explore the fact that at turn on, that's what I'm seeing. I've got no apparent distortion in the input signal on channel 2, but I've certainly got a lot of distortion appearing there at the output. So that would probably indicate to me something in the way that there's not enough base drive to this particular transistor, or the fact that this particular design, it has no emitter resistance. If it had a little bit of emitter resistance there to help stabilize the transistor, then we'd be seeing not quite so much distortion. Alright, look, I might take some measurements here then, using the multimeter, auto ranging DC, and let's have a look and see what we've got on the base. Yeah, look, I'm driving that fairly hard at 657 millivolts, and you can see my rail there is 9 volts. Got 9 volts coming from a regulated power supply. So I'd suggest that I've probably got that pot at the moment up toward the at the minimum resistance. Let's just have a bit of a turn on that. Ooh, there we've got a lot of, we've really super saturated that poor little transistor with 700 millivolts. And gee, look at the signal on the collector here. We've got a lot of clipping taking place as we increase that bias going into the transistor. Ooh, so too much bias there really starts to play havoc with that poor little transistor. And then by the time we get down here at about 0.67 volts on the base, things start to behave, but still look at that shocking distortion that I've got there, and now it's even more exaggerated, very broad at the top and very pointy at the bottom, and the lowest I can go is 0.65 of a volt drive on the base. So I don't know whether it's purely a lack of base current. I'd suggest that I've got a stack of base current flowing here. We could run the maths on that. If we took the resistance reading and we know the voltage there, we know the voltage at the other end, we could take VBE away from VBB and we could divide it by the total resistance, and we'd probably find that we've got quite a high value of base current flowing in that poor little transistor. If we look at the collector voltage when we've got the transistor hard on, comes down to just 80 millivolts. It's almost a short circuit. It is super duper saturated. That's VCE, of course, I'm measuring there. And VCE, we would normally want to run it around about, in this particular circuit, because there is no emitter resistor, and we've only got one resistor in the collector circuit, we'd probably want to run about 4.5 volts on that transistor, which would the DC Q point would be midway up the load line for the transistor characteristics. And that's probably about as good as what we're going to get. And you can see here I've still got that distortion. So there's no way of overcoming that distortion in this particular circuit. Now, just looking on the back of this board, I'll try and turn this over. And bit of a jumbled mess here. I've had to, because I've got a lack of 4mm leads to jumper things on the front, I've simply used alligator leads to hook things up across the back of the board. Now you can see that variable resistor, the small electrolytic capacitor, 1k ohm series resistor, 4.7k in the collector, and here's our BC109. The transistor, we've been measuring just now the DC voltage at the collector. There is also a electrolytic capacitor coming across from that collector and going down through a 4.7k resistor down to ground. Let's have a look at that. 2 microfarad capacitor. I have got that bridged across there. So in fact I do have, now have I jumped that? No, I did not. I did not jumper that across there. We'd have to have a think about the AC gain of this. If I did have a jumper from there to there, instead of the AC load resistor being 4.7k, it would in fact be half of that, be 2.235k. 2.35k if I had that connected to there under AC conditions, and I'll show that in the notes shortly. And in fact I will do that. I will get the alligator clip and I'll put that across. We might do that now and just take an observation what happens at the output of our little amplifier, because this will change the gain of the amplifier. So I'll just put that lead in there now across to the 4.7k. Ooh, we've got a bit of a jumble of wires here. Look, I might just move this wire. Some of these wires are pretty humongous, and they really tend to get in the way of small components, especially if you try and do a lab like this with surface mount board. Oh, really complex to use tiny little hooks to hook things across tracks. Alright, now note what's just happened to the output signal. It's pretty well dropped in halves. That's what I would have expected. That's with that 4.7k resistor. Again, that's with that 4.7k resistor being added to the circuit. And I'll just quickly disconnect that. And look at that, the gain has doubled. The output signal AC wise has doubled. And I put that on and it's halved. And that's because the AC resistance from the collector is 2.35k with these on, because think about it, I've got the impedance of the 9 volts is 0 ohms. The impedance of the, well, let's say minimal resistance, and the impedance of ground for AC is also a short circuit, so 0 ohms, minimal resistance. So this point and this point are exactly the same for AC conditions. So putting that resistor from the 2 microfarad cappy down to ground would be exactly the same as putting it from there up to there, or putting it directly across that, because the reactance of that capacitor at 1 kilohertz is going to be very, very low too, and that AC is going to be going swish swash, charging and discharging very rapidly the plates on that capacitor, causing effectively AC current to flow through it. The second part of this lab, the first part was of course to go through and look at the DC parameters as I've just done. And the second part is to go through now and add on a small oven to this transistor. We're going to put a couple of parallel resistors twisted across the transistor, get a second power supply, and then put about, I don't know, 10 volts or something across those resistors, cause them to get very, very hot and cause the transistor to heat up. As the transistor heats up, we're going to observe what happens at the collector of the transistor. And as we know, we're going to excite the transistor. We're going to cause the forward voltage to fall back to turn on the transistor. Transistor is going to turn on harder and faster, and therefore we have to see the collector voltage fall. Just going to put a calculator into the view here, and what I've done, I've added a little resistive oven across the transistor. I might just take that off there after I run this part of the experiment, and I'll show you that oven closer up. Just a couple of 180 ohm resistors twisted together. Now I need to find out the power that I'm going to be putting into those little resistors, because I don't want to cook them and cause a little smoke haze in the workshop here. That'll be the last thing I want to do. So what have we got? 180 in parallel, we've got 90 ohms, P equals V squared on R. So I'm running about 9 volts into them. So it'll be 9 squared divided by 90 equals, I've got about 0.9 of a watt. Let's call it a watt. They're half watt resistors. There's 2 of them in parallel. That takes us to a watt. I think we're perfectly safe doing that. Things are going to happen quite quickly here, so I'd better hook up the voltmeter. Ooh, I'm running out of places to put parts here. Let's see if I can put that behind there. There we go. We've got that behind there. And then I'll monitor the collector voltage there. We're back to where we were before. We've got 4.5 volts. And I think we're right to go. So I'll just get my power supply, hook up that resistor. Let's take a note what's going to be happening up here. Now these are AC coupled from memory. Oops. AC. Okay, AC coupled on channel 1 and AC coupled on channel 2. All right. So we're not going to see any shift of the waveforms on the oscilloscope. That's okay though, because we know that channel 2 is in the yellow, and we've got about 1.3 volts RMS of output there. And I've still got that 4.7K resistor hooked up in parallel with the output of the amplifier. Look, I might just take that off. We don't really need that on there anymore. We did already discuss about that, so I can take him out of the way. There we go. Then we've got a slightly bigger waveform on the output. So again, we've got no DC component here. We've only got the DC component on the collector showing here. I'm going to see, as this heats up, I'm going to see, let's just have a look and make sure that's in camera. Yeah, look, it's in camera. It's not really zoomed in as well as it probably could be. But let's see. Here we go. Alright, I've hooked up that little oven. And there we are. We've turned the load on. And as soon as that load went on, as soon as the load went on, we lost continuity with the transistor. Alright, there we go. Here's the transistor. The oven is getting warm. The transistor collector voltage, as we expected, is falling. We started at 4.5 volts and we're down to nearly 4 volts. and going down reasonably slowly. It's not quite as dramatic as some other videos I've done where I've got the hot soldering iron tip and dump the soldering iron tip across the transistor. Yeah, look, I might put a bit more voltage into those. We might just increase the power across that a little bit more, because we do have quite a bit of thermal inertia there to overcome. Here we go. So it looks like we're able to, yeah, with a bit more oomph. I've got about 14 volts across that resistance there now, and we've been able to pull the collector back down to 3.5 volts. Now, as the collector voltage is pulled down, and I'll just turn my oven back a little bit before we do see a smoke haze. Look what's happened to the output waveform. The output waveform has started to severely clip on the bottom because the Q point has slid down the load line towards the zero part of the load line, which is VCE off. And therefore we've got this negative clipping taking place. I'll turn that voltage and current to the oven off, and I'll just disconnect that little oven, and I'll hold it up here. You can get a slightly better view of how that oven was hooked up. Just a couple of small resistors there that I put across the top of the transistor. And this is exactly what happens in many circuits. We've got transistors that operate near other parts of the circuit, especially in regulated power supplies, where components can get very, very hot when they're adjacent to other components. And you can imagine with this particular circuit, with no way of automatically compensating for the DC bias point, as the silicon inside the transistor became hot and excited, the Q point shifted severely. We saw a 1 volt drop in the VCE of that transistor, and that caused severe distortion, clipping on the bottom of our waveform. That's pretty well all you had to do in this lab, and I do the similar lab with the collector feedback bias arrangement, with the emitter feedback bias arrangement, and then we take all of these concepts and we put them together to build up to the point where we finally get a voltage divider bias. And then we try the same type of lab with the voltage divider bias, and we find out we've got superb stability, and even as we heat the transistor up with our little oven, we don't get the same runaway characteristics in the transistor. Alright, this is part 4 of 5 for basic BJT biasing circuits with Greg Moore from New South Wales TAFE.